We have Mike Brokaw from the Ohio Department of Transportation. He's going to be discussing the Ohio Department of Transportation's experience with polymer modified joints. Mike is the Assistant Bridge Engineer of Operations for the Ohio DOT.
Well, good morning. Thank you, Jason. Thanks, Wisconsin, for having us. In about a week and a half, our football team in Columbus is going to be coming to Wisconsin. I hope they get the same red carpet treatment as I've received. So, my name is Mike Brokaw. I've been with the DOT for about 9 years, and before that I worked as a bridge inspector throughout the country. And today I'd like to share just our recent experience with polymer modified joints. These can be called asphaltic plug joints as well. I've seen them called a number of things. And this past summer we spent maybe 2 months looking at these, the spec, looking at our standard, looking at the field condition. You know, is there anything we can do to improve how these are functioning? Because we're getting mixed opinions on how these are performing on our state routes. So I just want to address 5 things with you today. The first is, what is a polymer modified joint? And the photo there on the right hand side of the slide is a polymer modified joint. It's got the thin plate covering the gap plate. Underneath the gap plate is a heat-resistant backer rod sponge to keep the binder from flowing underneath. And then the cross section of where all the material goes it's a rectangular cross section, and that aggregate binder mix that's being applied right there in the photo is really the beauty of the product. It's got to be durable enough for impact for traffic. It's got to be strong enough and elastic enough for expansion contraction. So there's a lot of moving parts within that. So we say in our standard, our bridge design manual, we want these to be used for small movement joints. They're small movements, so about 1.5 inch is what we've specified. The second piece, and this is probably one of the bigger pieces for us, is we're going to change how we look at expansion joints. We're going to change how we code them on the good, fair, poor critical scale. And that's going to be a change for our inspectors, namely. And then, where do we put these things? Where do we put them? Anywhere? Or do they perform better in certain locations and perform worse in other locations? So we'll talk about that. We'll also talk just a little bit about manufacturer specifications, some of the differences in performance within each of the ones that we use, and then where Ohio is going to go. So this is the roadmap for the next 20 minutes. The first one, what is a polymer modified joint? What is not a polymer modified joint? We looked at about 125 of these this summer, and we found a lot of miscode. Well, a lot for us. We found some miscodes where it was sliding plate, and we just put the polymer modified material on top of the sliding plate, and we're going to say that is not a polymer modified joint. So we found some things that are going to fall off, and we're going to code these as sliding plate. So this is in 2009, it was a sliding plate. In 2014, the inventory changed to polymer modified, and we're going to change it back to sliding plate. So we're going to fix some miscodes. Also, with expansion joints and our philosophy in managing these, there's 3 primary functions of an expansion joint to allow the structural expansion contraction of the actual bridge, number 1. Number 2, allow for the safe travel of public going across that joint. Number 3, if it's designed to be waterproof, it should be waterproof. We've focused on the first 2 and kind of disregarded the waterproof. We have a generic condition rating guidelines for our expansion joints. And this is not the AASHTO element level. This is not condition state. This is what we have a condition rating. This is the non-NHS structures. So the AASHTO element guide does hold up for polymer modifieds. It tracks leaking where it should, and it also tracks debonding, so the 2 major deficiencies. So we're going to change our condition rating guidelines, and we're going to move, if you can see that between the left and the right, the differences, we're going to move all the leaking down 1. And I think that we've been putting up with leaky joints for too long. So we're going to put that widespread leaking in the poor, no longer function as designed, even if it's structurally and truck traffic, the tires, it's safely bridging the gap. Even that. So we're going to move down the leaking down to poor, and maybe that's where we should have been. With our current guidelines, You can see we have about 1,000 bridges on the state inventory that has polymer modified joints. So it's a big chunk for us. We want these to do well for our small movement bridges. This is where we stand currently. I mean, it's plus or minus 1,000, but 1,000 makes it easy numbers. We have 700 of them that are in good condition. And when we have people internal, people external to the department say these are the worst joint since sliced bread, or the best joint, no, they're the worst joint since, don't ever put these in. And we look at our data and we say, well, we're a C minus right now. We're doing pretty good. We got 70% of them are good. And a quarter of them are fair, and then a smaller number are poor. So what's the difference? Well, if we change our condition ratings to disallow the leaking, we expect the pie to shift a little bit, where about half of them would be good. The fair would be the same number, but it'd shift around a little bit, and then the poor would grow because of the leaking, and the critical would grow as well. So we're predicting a little shift in our inspections and how we code these. So just to give you a visual, this would be a good before, and if it's watertight, it's going to be good moving forward. If this was fair before, it's going to move to poor. You can see the debonding on the right-hand side between the polymer and the asphalt there. So that's going to move from fair to poor. This one's also going to move fair to poor due to the widespread debonding. And this one has some of the structural cracking down there in the middle. This one would move down to poor. And on the left-hand side, we're effectively asking inspectors to hold off on giving the condition rating for expansion joints until they look underneath. And if they see widespread dampness, moisture coming through, especially during the rain event, they're going to bring that down to poor. So these would be moving from fair to poor on the left and the right-hand side. And then these would be moving from poor to critical. Anytime the inspector will see a steel plate, we're going to move that down to critical. And the photo on the left is a common deficiency we see when the profile is too high. You get the plow chops. In the winter, the profile shouldn't be higher for the plow to catch, but sometimes due to the angle of the blade and the angle of the joint and the higher profile, if you put too much binder on top, we will get plow chops, and that's gonna hurt the bridge, or hurt the joint, obviously, and then the bridge. The layers of patches on the right, there is a steel plate you can see there. We're going to move that down to critical. So that was how we're going to change. We're going to change how we look at these things. The third place, well, are we putting them in the right location? Should we be putting them on big movement? If we're requiring these, or our standards saying use them for 1.5 inches, are we setting these up for failure, for an early demise? So steel beam, probably not. Interstate, we'll see. What I want to show you is, not the answer, but I want to show you what our data shows, and maybe offer some tipping points. So the first one we have, the first trend that we saw in our data was overall structure length compared to current condition. And on the left hand, that bar is bridges that are 25 to 150 feet long. And you can see the gradation. The green is good. Yeah, I think you could see that. And then on the right hand side is 150 foot or more structure length. So which do you think we use? Where do you think we use these joints, and which ones do you think are performing better? I think it's obvious we're using these on small movement structures, and that's where they're performing the best. 73% good, 3% poor, and this sample was 1,000 bridges. And then on the right-hand side, we've got the separation where 42% of that's poor, but it's a much smaller number overall. So we did this with our data, and we started seeing where the tipping points are, and that's kind of what I'm going to share with you here. We did have some outliers. An outlier that we found with polymer modifieds is if it's in a turn lane or at a street light, stop, start, you get the rutting, you get the increased polymer kind of sliding and sloshing inside there and tearing itself to pieces. So that's an outlier we saw. Even if you put it on a small movement joint, it will likely tear itself apart in the turn lane. Also, if you put on the right bridge, this is a good structure to put this on. We found this as an outlier, steel plate exposed and layers of patches on a bridge with small movement. We're wondering what on earth happened there? Is this some anomaly? Well, when we looked at the inspection records, the inspector correctly put in the date of install, and the date of install is 1999, and this is a 17-year-old polymer modified joint. And once we add date into the data, this is not an outlier anymore, right? 17 years is longer than what we'd expect. We looked at things that were really inconclusive. We looked maybe bridge width. they're tearing themselves up because the joint was too long, the bridge is too wide. And if you look at all of our structures, we're using these between 30 and 50 foot width on bridges that are between 30 and 50 feet wide. There's really no outliers, nothing that we could draw from this other than we're using them on the 2-lane. Skew was also inconclusive. We're using them more on the less than 10-degree skew, but there's no big separation, so to speak. Then we looked at ADTT and ADT, the truck traffic. We found a tipping point right around 1,000 ADTT, where we have 75% good and 3% poor. And on the right-hand side, it begins to separate where the good is less than half for ADTT greater than or equal to 1,000. And our tipping point for ADT was about 9,000. Now, I'm not going to say don't use these on ADT greater than 9,000 or ADTT greater than 1,000, but it's just good to have appropriate expectations for the joint location. And this is not to say this is a joint that can't be used on higher ADT. It's just this is what our data is showing. An outlier, well, we have the age factor come in. This is interstate polymer modified joint. It's in good condition. Well, it's new. So once we add the age, that's no longer an outlier. So this is a brand new polymer modified joint. It's functioning well. It's on the interstate. We're going to see how long it functions moving forward. So the last data piece we looked at was a functional class, and it pretty much matches ADT, ADTT. The tipping point for us was the principal arterials. That's when we started to get that separation. Fourth, we looked at manufacturer specifications. This is a screenshot. You might not be able to read from the back, but we have a qualified product list, and we have 5 qualified products for this joint. The Matrix, Craftco Matrix 502, we use that. The DSA Thorma joint, we use that. And the Wabo Expandex Watson Bowman, we use that. So those are the 3 that we use. And this is what our data shows for those 3 suppliers. We use, some obvious things. We use Craftco, the 502 more. You can see that. That's the tallest there. And it's these are percentage-wise. These are performing well or as expected. We've got, just to show you the percentages, 85% of the ones DSA's put in the last 6 years are still good. And we use 6 years just because that's the data we have. This is not the entire 1,000 bridges. This is just 300 of them. So this is not the complete sample. This is just the last 6 years. So 85% good, 2% poor, 68% good, 7% poor, and 60% good, 3% poor. So that's the last 6 years and how our suppliers are doing. And we kind of wondered, if you remember that pie chart, we had 70% good. We wondered, well, why is DSA outperforming the 70%, and why do we use so little of Watson Bowman, and why do we use so much Craftco? So we had a lot of questions. We're wondering why this is the case. So it has a lot to do with their specifications and the joint movement that we would expect, and how they're set up internally. So we looked into the specifications just to see if there's anything objective that we could compare. And we landed on the aggregate in a few different ways. The aggregate, how it's graded, just because the 502 and the Thorma joint were the most prevalent. I highlighted those black there. And it looks like, just graded wise, that the aggregate's important. And it's not just, it's not limestone or anything. It's granite. It's really hard aggregate because it's got to really transfer that load through the joint. Aggregate or basalt. I've seen a few other rock types, but they're pretty similar. If you look into the weeds, look into the details, you could say that DSA is a little more graded, and that would just this aggregate would fit together better as a puzzle piece. It would interlock a little better and distribute that load a little better. And you could also say that there's a potential for less dust in the DSA, and the dust, just imagine a pizza crust, pizza dough with too much flour, or the polymer modified with too much dust. It might not get that binder around the aggregate like you need. So there's, currently our spec says we leave it up to the manufacturer specification. We're not experts in these joints. We don't pretend to be. We're just looking to see where we could see any way to improve the quality in the field. The way the aggregate's heated, just to compare the two. DSA has got a double batch. The first barrel is a vented drum, and there's a potential for blowing out even more of the dust. And it goes into the second drum. It's heated to get those impurities out. Water is a bond breaker. Whereas the 502, it's a one batch, and there's a potential for more dust in there. And so our supplemental spec, we've been scratching our head for a number of years now. 2013, we required the manufacturer representative to be on site. And that didn't work out that well, just because of how much we put in and some of the authority conflicts that we would have in the field if someone has a subcontractor installing these. So we scratched that. In 2015, we said, well, okay, we're on the same team, right? We want these joints to work, and you want these joints to work. How about we just require a quality control plan? And whoever's installing it in the field, you sign off on the manufacturer specifications to give us confidence that the aggregate was at the right temperature, the binder was evenly coated, and we had the proper cleaning of the tank. That's where we are now. We changed it in July 2015, and moving forward, we're going to wait. We're going to change our inspection guidelines, and we're going to wait at least in a full inspection season to see what the change is, to see if there's anything more that we need to do. But in the future, we're wondering if we should hunt for the gaps in our spec and see if there's a way we can address the means and methods or aggregate. We don't know. We're scratching our head on it as well. And we're working with suppliers and industry and the people writing our specs. We're writing them, but the people writing some of the specifications for the industry. So in conclusion, we're going to keep using these. We like them. Our construction inspectors know what to look for. I think the data shows that they're performing well in Ohio. We do need to up the training. We do need to up the quality control because of the on-site batch mixing. Anytime you do that, you open yourself up to quality control issues. So I think that can be addressed with training, everybody getting trained. We're going to update our inspection manual, as I said. We're considering adding 2 fields, the joint date and the joint supplier, to our inventory. I think that might help us track age and supplier and see in real time, see how these are performing. And we're going to consider editing the supplemental specification 846 again. So that's kind of in a real tight nutshell, that's where we have been with our polymer modified joints. And I don't know if I'm taking questions now or.
Yeah, we have a couple minutes for questions if anyone has any.
Did you do a similar study with your other joint types that you use? Whether it's strip seals or other things, just to compare the 2 different joint systems, or more than 2 different systems?
Yeah, we did not compare, but this is leading me to want to look into, better our current inventory, what's currently performing, what's currently outperforming. Didn't do it. This is pretty fresh off the press, so we are going to continue the investigation. Yeah, good question.
Mike, when the joints start to fade, are the ODOT folks able to do any repair work on any of these joints?
Yeah, that's one of the things that we wrestled with the leaking. And what we would do is crack seal and for the debonding, and that would theoretically move the condition up if we change it to leaking. We can, I don't know if it's a correct way to do it, but it does stop the leaking if we crack seal debonding. We do have hot mix or throw and go going in the spalls that we see. You saw some from the photos. So we can put Band-Aids on it, but I don't know if it's truly addressing the root cause. Yeah.
After studying the data, what is your expected life out of the joints? Do you have a life expectation for different ADT, or I guess I'm curious when you're programming, what you go in with.
Mm-hmm. We'd like to get it a paving cycle. So for us, that's somewhere around 7 years. We had the same question, should we be putting these on the interstate? They're not lasting 10 years on the interstate, but if they're put in correctly, you know, with all the right controls, they can last 7 years on the interstate. We've seen them. I mean, just like if you have a big enough inventory, we see outliers on either side, but the majority we're getting more than 7 years on these. If you look at the last 6 years, most of those are good. So we're getting, you know, if we just look at a snapshot right today, they're lasting longer than our paving cycle, which is what we want.
All right, we'll take one more question.
Based on your data there, are you considering opening up these joints for higher skews than what your guidance currently allows?
No. Our current guidance, specifically for polymer modified, is just expansion, open 1 inch, 1.5 inch opening. I think the right spot for these is the 50 foot or less wide, low skew. We want them to last long, but sometimes we don't have the luxury of putting in what we want to put in. So this often does go into the higher skew if we have to put it in. But I think we're going to treat that as not preferable. Yeah.
All right, thank you very much, Mike.
Yeah, thanks.